Hello and welcome to this video about the Weierstrass M-Test. This is a topic from real analysis, so if you want to learn more, you should check out my real analysis course. However, before we start with this M-Test, I really want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with the link in the description, you find additional material like PDF versions, quizzes and other stuff. Okay, with this, I would say we can immediately start explaining the Weierstrass M-Test. Now what you should remember is that this M-Test is a comparison test for series, but for the uniform convergence for a sequence of functions. So it's not so complicated at all, and it's called M-Test simply because the constants in the theorem are called M. And there I would say we can immediately formulate this statement. And as already mentioned, the only thing you need here is to know what a series is and the uniform convergence for a sequence of functions. And these functions can be defined on any set, so let's call it D. And indeed, often we have that D is a subset of the real numbers. Hence, our functions fk should have D as their domain. And now the functions could be real valued or complex valued. So in general, we could just write that they map into the complex numbers. And then we have a function for each k in the natural numbers. So already a whole sequence of functions with the same domain D. However, for the Weierstrass M-Test, we are interested in the partial sums, so the series of these functions. And to have the convergence of this series, we assume that we have constants with the name M. And as already mentioned, this is the whole reason we call it the M-Test. Now we have two assumptions for these constants. First, they should be non-negative, and second, the series should be convergent. This means that the limit of the partial sums should exist. In other words, the value of the series is not equal to infinity. And now in addition, the constants should be always bigger than the values of the functions fk. More precisely, we look at fk of x and take the absolute value of this. And then this should be less or equal than mk. And indeed, we want that for all k in n and for all x in d. So the constants mk form a uniform majorand for the functions. Okay, so these are the assumptions we need, and then we get the result for the series of the functions fk. Indeed, by the comparison test for series, we immediately get that the sequence of partial sums converges for every x in D. However, we get even more because we deal with functions. The term uniform convergence also makes sense. So we get out that the series is uniformly convergent. Moreover, as a side note, I should also mention that we have the same result for the absolute value of the functions. So both nice things come out of the Weierstrass M-Test. Now in the case you don't know exactly what the term uniform convergence means, let me refresh your memory here. Now the first thing you should see here is that we get a well-defined function we can call capital S. And this one has the same domain D and it sends x to this series. And what I mean there is that we just sum up fk of x. And this limit should exist, so we get a well-defined function S. And moreover, this capital S is the limit of the partial sums of the functions fk. And when I say limit, I mean with respect to the supremum norm. And please recall, the supremum norm is usually denoted with this infinity sign on the norm. Now S is the uniform limit for the partial sums, so this goes to 0 when n goes to infinity. Hence, this is exactly what we mean by the uniform convergence stated in the theorem. And maybe it's always good to visualize this convergence in a picture, so let's sketch the graph of the function S. And let's simply say that here on the x-axis we have the domain D. Hence, for example, the graph of S could look like this. And now what one can do is to look at such an epsilon tube around this graph. And then the result is, no matter how small we choose this epsilon, the graph of the partial sums always lies inside. Obviously, this only has to hold eventually, which means n has to be big enough. So this is what you can remember, this is exactly what the uniform convergence means. Okay, then the next step would be to look at the proof of this statement. And in fact, it's surprisingly easy. We only need the so-called Cauchy criterion for series. And you can find that in my real analysis course in part 17. And it simply tells us that a series is convergent if and only if the partial sums form a Cauchy sequence. So you see, the Cauchy criterion simply uses the completeness of the real or complex numbers. Now more precisely, this means that for all epsilon greater 0, we find an index capital N, such that for all indices afterwards, and let's simply call them lowercase n and m, we have that the sum in the absolute value is less than epsilon. And the sum has to go from m to the index lowercase n. So you could just say this partial sum is arbitrarily small eventually. And now please recall, in the assumption of the theorem, we assumed that we have the convergence for the series of mk, which means we have the Cauchy criterion as well. Hence, for a given epsilon greater 0, we can choose a capital N as above. And then we immediately get a result for the series of the functions fk. So let's simply look at the partial sums from m to n as well. And then we can just use the standard triangle inequality. It's a finite sum, so we can just pull the absolute value inside. And then in the next step, we can just estimate fk of x inside. And now the assumption comes in that we know that each one is less or equal than mk. However, for the series of the non-negative mk's, we already know it's less than epsilon by the Cauchy criterion. In other words, the Cauchy criterion now also tells us that this series here is a convergent one, which already implies that the function s from above is a well-defined function. In other words, it exists and it makes sense to talk about it. And that's what we will do now, because we want to talk about the supremum norm. More concretely, we want to take the difference of s with the partial sums in the supremum norm. And exactly like before, let's fix an epsilon greater 0 and let's choose the corresponding index capital N. And as always, the lowercase n should be greater or equal than this capital N. Now first, as a reminder, the supremum norm is given by the supremum. So instead of the norm, we can just write supremum over x in D. And then we just look at the absolute value of the functions. In other words, we just put in x at the correct positions. And then, in the next step, we can simply substitute s of x with the limit definition. This means, instead of the infinity symbol here, we can just write limit of the partial sums. So maybe let's use a number m that goes to infinity. And now we can simply use that the absolute value is a continuous function, which means we can pull out the limit. So it's not a problem at all to write the limit in front of the absolute value. And then you should see, inside the absolute value, it looks much simpler now. We just subtract finite sums, so we know a finite sum remains. However, maybe it's not clear how to write the sum, because we don't know if m or n is bigger. But obviously in the case that m is bigger than n, we would say that k goes from n plus 1 to m. And of course, in the second case, we would just write it the other way around. It does not change so much because we know for both cases, if n and m are bigger than the capital N, then this whole sum is less than epsilon. This is simply the Cauchy criterion we have at every point x. Hence, the conclusion is, even with the limit and with the supremum, we stay lower epsilon. The only thing we can lose here is the strict inequality. But obviously this does not change anything, because epsilon was arbitrarily chosen from the beginning. And with that we have it. This means that in the limit n to infinity, this norm here goes to 0. And since we have the supremum norm, this is exactly the uniform convergence. Therefore, this is already the whole proof. And then I would say, let's look at a nice application of this Weierstrass M-Test. So let's take an example of a series with a function inside. And if you know something about Fourier series, you might recognize that this one here is an important one. So let's take fk from R to R, where fk of x is given as the cosine of kx over k squared. So this is our function depending on k, and now we can look at the absolute value. And we know that the cosine is bounded by 1, so this is definitely less or equal than 1 over k squared. And this holds for every x in R. And now you only have to know that the series of 1 over k squared is convergent to apply the Weierstrass M-Test. And there are different possibilities to show this, but it's definitely not too complicated, and a basic result you definitely should remember. And indeed, we can immediately make use of that with the Weierstrass M-Test. Our conclusion is that this series of functions is uniformly convergent. And indeed, this is really helpful as a result, for example, when you want to calculate the derivative of this function. And something like that you can find in my Fourier transform series. In fact, exactly this result here plays a crucial role there. Okay, then I think this is good enough for this video, and I really hope I meet you in another one. So have a nice day, and bye bye!